Hi everyone, I just wanted to show you this code that I made when I taught linear algebra in person last semester. It has to do with the mouse maze, and you all got the matrix correct, and here it is, you can see. Now the language of this particular code is in SageMath. SageMath is pretty much built on top of Python. I will share this code with you as is, but if you don't have SageMath installed on your computer but you have Python, you may want to put it in AI and ask AI to convert it to native Python. So here we have our transition. These are the rows of the vector, and I put them all together in a matrix called A, and I start our initial vector with the mouse being in the first position, as you can see here. And I'm going to say, let's do 50 iterations. And the whole reason to do this is I thought it would be interesting that you would see some visual output of how the transition matrix, how each new generated transition matrix changes over time. So when I run this program, you can see the evolution of the vector component over iterations. And you see our first iterations take you with equal probability to x2 and to x4. So I can go ahead and play this, and we can see the iterations. Each one of these iterations represents the probability of being in the specific room denoted by the position vector. So as we get closer and closer to the iterations, they change less and less each time. And here we have the final print. So basically when you run this, it shows you the final position right there, and that allows us to see it by iteration. So let's go ahead and we'll change the iterations to 100, and we'll hit run again. It takes it a while to do. And here's our start. We already see our end result is very similar than it was last time. And if I could hit play, it would be a good. And we can see it just evolving exactly the same as we did before. But we see that the probability for some of the rooms changes drastically. It shouldn't surprise us that the fifth room has the greatest probability of being occupied, even throughout all of the iterations, because it has more entryways to it. And as we notice, the vector is slowly changing very, very little. So we're actually discovering, if you read up this particular method, there is a method similar to Markov chain iterations, where we actually find eigenvectors of a given matrix by computation rather than by doing the diagonalization or finding the null space with a minus lambda I, etc. So here it is. I'm going to give it to you to play with. I'm not for sure what this is down here. Maybe I can final vector after the iteration. So this final vector, okay, let me do this. So I'll just let you play with this, and notice that the final vector are given as exact. So this is an exact number right here. It's a fraction. Right there is the division line. And here's the numerator. And I was trying to look to see if there's an easier way to do that so it actually outputs it as decimal numbers, easier for you to see. At any rate, I kind of just showed you, all I wanted to do in this video was to show you how to open up this, see what it does. You can experiment with it. For example, you can experiment with different initial vectors. Suppose you want to start at position 4. Then you could see what the iterations do over time. Now you see I have it right now fixed at 100 iterations, and it takes a while to compute things. And here we go. Here's our final vector after 100 iterations, and this is in decimals right here. You can see what it is, and we'll go ahead and play it. And you see there's, when we started, the fourth vector, it really jumps and changes quite a bit through each iteration. But as the iterations continue on, they slowly settle down into a more stable final vector. And that's what I was asking you to compute, is to compute the difference between iteration 30 minus iteration 39, for example. I don't remember the exact numbers. Anyway, play around with it. It can be fun. You can't mess, you can't hurt anything. You can change these. You can actually change this so it's no longer a Markov matrix. Suppose I put 1/3 right there. So I know it's no longer a Markov matrix because the columns don't add up to 1. But let's run it anyway and see what changes. Well, it changes quite a bit, and probably because the scaling is way off now. Although they seem to be rising up. Really interesting change here. This is supposed to be the end result, but could it possibly rise up that much? All the way to 8? I don't think so, unless it does so at the very last. We're in iteration 70. It could. We've got 80. Yeah, it's growing really fast. How interesting. Quite interesting. Anyway, I'm going to stop this recording and let you all play with it. And I wish we could do a lot more in class with computational methods like this, but we can't assume that people know how to compute in any language. But I'll share this with you. If you know how to code, you can play with it. If you don't know how to code, then you can run it by basically installing Python on your machine, taking the code, and having AI change the code for Python, so you don't have to do Python and Sage.